Okay, I'm going to draw some pictures to illustrate these four different cases. The way I'll draw the picture always is having x, the state variable x, against the parameter mu. So these changes occur as you vary mu. So imagine that you're looking at a fixed value of mu because mu is a parameter, and so mu doesn't change except that you're going to look at different cases of mu. So you're going to think of different values of mu and want to understand what happens to the changes in the structure of the dynamics in the x variable as you take different mu's, all right? But mu does not change with time. So here's the first case is where the curve, say, looks something like this. So there's a particular value here, mu naught, opposite which the fixed point disappears. So you imagine you're sort of following this fixed point here to the left. I'll do that in red. And you suddenly get to this point, this parameter value mu, and then after that, the fixed point actually disappears. So but the problem is that the curve of fixed points actually carries on, but it carries on back to the left, right? So it sort of turns around. And this is what is called a saddle node bifurcation. You'll perhaps understand in a minute why it's called a saddle node bifurcation. This is the case where they disappear, and in some sense, as I say, that's a sort of collision of eigenvalues. The second case is the case where you got a fixed point going along here. So this is the curve of fixed points, right? And then another fixed point comes and sort of crosses it, so like that, right? This is called a transcritical, right? Where your fixed point is trotting along as you vary mu, and then you get to a certain value mu naught here, at which another fixed point crosses it. Right. The third case is what's called a pitchfork. So here the fixed point keeps on going. This is mu against x, but coming out of it at a certain parameter value mu naught. Sorry, let me erase this line here. At a certain parameter value mu naught, emerging from it, right, is another set of fixed points, and I'll draw that here in terms of that. So emerging out of that are actually two fixed points, because you see you've got to sort of draw continuous curves here. So if one fixed point comes out, well, there sort of has to. It turns out there have to be two, at least in a sort of nice generic situation, and that's called a pitchfork bifurcation. Okay, and then the last case is the case where a periodic orbit comes out. So this is a little bit harder to draw because it requires higher dimensions. So when I draw it, I can't quite draw it in the same way. My state space x. Sorry, I'm going to sort of start again with that. My state space x. Okay, so the state space has to be now actually two-dimensional rather than one. So I'm going to draw it like this, and this is x1, x2. So that together makes x. And then I got a parameter mu. So you want to imagine this happening in three-dimensional space. And then I've got this curve of fixed points here, but coming out of that at a certain parameter value here is a periodic orbit. And what we're going to do is sort of draw that as kind of a sort of parabolic type structure like this, emerging from it. So this is at this parameter corresponding to this parameter value mu naught here. At that mu naught, the fixed point carries on for larger mu's, but coming out of it, there's going to be a periodic orbit. So the idea here is, remember again, what you want to do is you want to think of frozen values of mu, and at that value of mu, go up and look in the state space x, and this will record what kind of fixed points you have, or what kind of periodic orbits you have, right? So this is what's called a Hopf bifurcation. Okay, what I'm going to tell you in the next thing is how you know when these situations occur.